Imagine measuring a room full of people. For each person, you jot down their height, their weight, their arm span. But these three numbers are not really independent. Taller people tend to weigh more and reach further. Almost all of the variation is just one hidden thing: overall body size, dressed up as three columns. Now push it further. Suppose each point carries 50 features, most of them tangled together. We cannot picture 50 dimensions, and many columns are near duplicates. So here is the real question. Can we replace 50 features with just a handful of new ones and still keep almost all of the variation in the data? That is exactly what principal component analysis does. It reduces the number of dimensions by building new axes that line up with the directions the data actually spreads along. Let's see those directions. Here is a cloud of data on the plane, a tilted, oval blob. It clearly runs further one way than the other, but along no axis, you were handed. Not the x-axis, not the y-axis. First, find the balance point, the centroid, the mean of every point. Everything in principal component analysis is measured as spread around this center. Now sweep a line through the center and ask, along which direction is the spread the greatest? That winning direction is the first principal component, PC1, the long axis of the oval. The second principal component is fixed by two rules. It captures the most of whatever spread is left, and it stands exactly perpendicular to the first. Here it is, the short axis PC2, to perpendicular axis, ranked by how much the data varies along each. The long one holds most of the story, the short one, very little. That ranking is the whole engine of the method. So we have our best direction, the goal line PC1. To reduce the data to a single dimension, we drop every point straight down onto it, the closest point on the line to each one. Watch the perpendiculars fall, and every point slide onto the line. A two-dimensional cloud becomes a one-dimensional string of points. But look how much of the original spread survives. The long axis is preserved almost perfectly. That single surviving number, how far along PC1 each point landed, is its new coordinate. We threw away the second dimension, the tiny sideways wobble, and kept the direction that mattered. That is dimensionality reduction, done right. So how do we actually find that best direction without guessing lines one by one? The whole method is 4 clean steps, and it rests on a single matrix. First, center the data. Second, build the covariance matrix, sigma. It packages every variance and every pairing at once. 1 over n times x-centered transpose times x-centered. Read it like a table. Each diagonal entry is the variance of one feature. Each off-diagonal entry is the covariance between two features, how they move together. And because pairings are symmetric, sigma equals its own transpose. That one fact is about to hand us everything. Third, and this is the beautiful step, take the eigenvectors and eigenvalues of sigma. Because sigma is symmetric, its eigenvectors come out perpendicular, exactly the ranked axis we were hunting for. Each eigenvector is a principal component, a direction, and its eigenvalue is the variance the data has along that direction. Big eigenvalue, big spread. The eigenvectors point the way. The eigenvalues tell you how much. Fourth, sort the eigenvalues from largest to smallest and line the eigenvectors up to match. The biggest is PC1, the next PC2, on down. Then keep only the top k directions and project each point onto them. Every point turns into just k numbers. Its coordinates along the strongest axis. From d dimensions down to k, holding on to the most variance possible. The eigenvalues do more than rank the axis. They tell you the price of dropping each one. The fraction of variance a component explains is simply its eigenvalue divided by the sum of all of them. Add those fractions up as you include more components, and you get the cumulative variance explained. because the total of the eigenvalues is exactly the total variance in the data. These fractions always run between 0 and 1. Plotted, it becomes a scree chart. The gold bars are each component's share of the variance, falling off fast. The first bar towers over the rest. That steep drop is the signal that a few components carry the load. The green curve climbs to the cumulative total. You pick the number of components, K, where this curve first crosses a comfortable threshold, say 90%, right where it starts to flatten. That is how many dimensions you keep. Let's grind every number by hand. 3 data points, 1, 2, 2, 3, 3, 4. Step 1. Center the data. The means are 2 and 3. Subtract them, and the points become -1, -1, 0, 0, and 1, 1. Step 2. The covariance. Sum each centered point times its own transpose. The middle point contributes nothing. The outer products of -1, -1 and of 1, 1 are both all ones. Add them, divide by 3, and sigma is 2/3 in every slot. Step 3. The eigenvalues. Subtract lambda down the diagonal and take the determinant. 2/3 minus lambda squared minus 2/3 squared. That simplifies to lambda squared minus 4/3 lambda, which factors as lambda times lambda minus 4/3. So the eigenvalues are 4/3 and 0. For lambda equals 4/3, the equation says 2/3 of a plus b equals 4/3 a. So b equals a, the direction 1, 1 normalized by root 2. That is PC1. The line y equals x. The 0 eigenvalue gives the perpendicular direction 1, -1. And the variance explained by PC1 is 4/3 over 4/3, a full 100%. And that makes perfect sense. Those 3 points sit dead on a straight line. So there is exactly one direction of spread. PC1 captures everything. The second component is pure 0. The same idea lives just as happily in 3 dimensions. Here are 3 axes and a cloud of points floating in space. But watch as the cloud turns. It is not a solid ball at all. It is nearly flat, a tilted pancake. The points spread widely 2 ways, and hardly at all in the third. Principal component analysis finds the 2 directions. The pancake spreads along, PC1 and PC2, drawn in gold and green, and it finds the thin direction across it, the third axis, where there is almost no variance at all. To go from 3 dimensions down to 2, we squash that thin direction to 0, projecting the whole cloud onto the flat plane it already almost lived in. Every point drops onto the pancake's surface. 3 dimensions became 2, and almost none of the spread was lost, because the direction we dropped never held much to begin with. That is the entire promise of PCA, seen in one picture. A second example, the kind you meet most often. A 3-dimensional dataset has a covariance matrix whose eigenvalues are 6, 3, and 1. No matrices to diagonalize. The variances are handed to you. First, the total variance. Just add them. 6 plus 3 plus 1 is 10. So the first component explains 6 over 10, 60% of everything, all on its own. And the first two together explain 6 plus 3 over 10, 90%. So choosing k equals 2 takes you from 3 dimensions down to 2, while keeping 90% of the variance. A superb trade. Your turn. A 4-dimensional dataset has covariance eigenvalues 8, 5, 4, and 3. Pause the video and work out what fraction of the total variance the first principal component explains. I'll wait. Here's the walkthrough. The total variance is 8 plus 5 plus 4 plus 3, which is 20. So the first component explains 8 over 20, that is 0.4 or 40%. And the first two together reach 13 over 20, 65%. If you got 40% for PC1, you have genuinely got this. Trap 1. And the biggest, forgetting to center. Skip subtracting the mean and the covariance picks up the mean shift. So the principal directions come out wrong. Always center first. Trap 2. Ignoring scale. If one feature is measured in meters and another in rupees, the large-scale one dominates the covariance. When scales differ, standardize, divide each feature by its standard deviation. Trap 3. Expecting PCA two separate classes. It is unsupervised. It only chases overall spread. It can happily flatten the very direction that told two classes apart. That job belongs to a supervised method like LDA. Trap 4. Confusing this with feature selection. Principal components are brand new features, linear blends of the originals, not a subset of the columns you started with, which also makes them harder to interpret. And trap 5. Worrying about an eigenvector sign. If V is a principal component, so is minus V. They point along the same axis. The sign carries no meaning. Let's lock it all in. Center the data, build the covariance matrix sigma, and take its eigen decomposition. That is the whole pipeline. The eigenvectors are the principal components, the ranked directions of spread. The eigenvalues are the variances along them. Keep the top k components chosen so the cumulative variance they explain is large. That is your reduced, faithful representation. And one elegant footnote. Doing exactly this is the same as taking the truncated singular value decomposition of the centered data. Master these 4 lines, and dimensionality reduction is yours.